And so let's look at a simple example of a finite state machine. Now, many of these things, of course, you guys are familiar with. And but however, I have found that sometimes it is necessary to refresh memory because you may have done it a while ago. And also, time to time, I'm bringing out some specific things that we will talk about. So maybe I should make it a little bigger, this table. So here is the state table. And let us assume that in this state table, now people organize their state tables in different ways. Let us assume that we have one input x, and we have four states, 1, 2, 3, and 4. So these are the four states. And input x can be 0 or 1. And in here, let me have entries. Are going to be next state and the output. N is for the next state. So let's assume that the next state for this combination, that means when the state is 1 and input is 0, happens to be 2, and the output, when the current state is 1 and the input is 0, is 1. And let us assume that it is given, let's say I'm doing some kind of design, and as an intermediate step during the design, I come across this. And let's assume that it is given that in this case, the next state is 3 and the output is 0. There is one output. Let's call it Z. 2, 1, 4, 0, 1, 0, 4, 0, 3, 1, 3, 0. So let us draw a state diagram using this state table. So here's how the state diagram will look like. So we will have the four states. Let's start with state 1. Maybe we'll put it here. Here is state 1. And so from state 1, we go to state 2. Let's assume here is state 2. When the input is 0 and the corresponding output is 1. Now, different people use different formats. This is a lot of people do this. So basically, we are saying that this is the input, and this here is the output. So notice what we are saying here is that when input is 0, you will go from state 1 to state 2. And also we are saying that when you are in state 1, and when input is 0, the corresponding output is 1. So actually the output is associated with the state. Output is not associated with the transition. But this is just a convenient place to specify the output. Because you want to specify the output for all possible input combinations, so this is a convenient place. Now for state 2, if the input is 0, you stay there with the corresponding output of 1. And for state 2, when input is 1, you go to state 4. Let's have it somewhere here. This is a state diagram. Okay. So here is 4. And and when we are looking at state 2 here, so 2 comma 1, so when input is 0 and the corresponding output is 1, and so that takes care of all the possibilities for state 2. Now let's work on state 3. Now for state 3, when input is 0, you go to 1, and the corresponding output is 0. And when input is 1, you go to state 4, and the corresponding output is 0. And finally, to take care of state 4, you go to state 3 when input is 0, okay? And the corresponding output is 1. And you go to state 3, again, I could make 2 of them, or I could just make 2 of them, but I could just put 2 labels on the same transition, same thing. And this is 3 comma, this is, oops, sorry about that, bad label there. Input is 0, output is 1, and input is 1 and output is 0. I hope you can see. Can everyone see the diagram? Is it too small? Can you see? Okay. I guess sometimes since I'm standing so close to the board, I can see everything clearly, but you are sitting a little bit away, so sometimes I forget about that. So this is an example of a finite state machine. And now we can continue this example. Now let us assume that we apply some input sequence. Then how will the circuit respond? Responds to an input sequence. And notice, I'm using the term input sequence. That means we have an input, next clock period we have another input, 0 or 1. Next clock period we have something. So let us assume that we are going to be specifying input, which we are calling x, and let us assume that here we are going to specify the state, and here we are going to specify the output. And let's assume that during 1 clock period, the input was 0. The value sampled in the next clock period was 1. Value sampled in the next clock period was 0, and so on. Now, is that enough for us to find out how this will respond? If input is 0, what is going to be the output? Well, since it is a sequential circuit, you have to know what state this is in. And let us assume that it is given that you start in state 1. So basically, this part is given. You have to know the initial state. If you don't know the initial state, then it will be very hard for you to figure out how the behavior is going to be. Now, usually that is not a problem, because practically always you have some way of resetting the state of any sequential circuit. So if the state is 1 and input is 0, what is the output? State is 1 and the input is 0, the output is 1, and the next state is 2. So notice that this is how we get the calculation. Right? Notice that the output depends on the present state. So this is the output, and it depends on the present state and the current input. So this is how it is, and this is going to be the next state. Okay, when the state is 2, and what happens when input is 1? State is 2, input is 1, next state is going to be 4, and output is going to be 0. And you can figure out that when state is 0, when you are in state 0, if the input is 0, then your output is going to be 1, and so on. So this shows the response to an input sequence. So here is the input sequence. And here is the response to an input sequence. So notice that whenever the behavior is sequential, you need to apply, if you want to test it, you need to apply a sequence of input values, and you need to observe the output sequence. In case of a combinational circuit, it doesn't matter in what order you apply the inputs. For a given input, you know what is the behavior, but in case of a sequential circuit, you have to know what state the sequential circuit is in, which makes testing of finite state machines interesting. So later we are going to talk about testing of combination circuits, and we will talk about testing of sequential circuits. Okay, so far we have talked about mostly lower level things, gates, flip-flops, and let me mention about large combinational blocks. So for example, let us say if you look at a picture diagram of a processor, which are also called microprocessors if it is implemented using a single chip. And these days all the processors, they on this single chip. In fact, on the single chip, now it is common to have multiple processors. So these are the things you may find in a processor. So in a processor, you will find some parts. And that means lines, buses, networks, things like that, through which information moves. And then you have combinational blocks. So you can have some random logic, some bunch of NAND gates or AND gates and OR gates, inverters, programmable logic array, or ROM is also a combinational circuit. So basically a combinational block that has no memory. So a combinational block doesn't have any state. There are no storage elements in there, as opposed to a sequential block. Now, example of a sequential block could be flip-flops. Then you have registers. Basically, a register is a row of flip-flops with a little bit of logic, and then you can have memory. a memory basically is an array, is a two-dimensional array. So if you have a register would look like this. So this is a register.